in all likelihood, you already have done regression. Simple linear regression where you have only one dependent variable like price of a house and square feet. In multiple linear regression, we have price of a house depends on bunch of things. Square feet, lot size, number of bedrooms, and etc. We're going to do logistic regression here. It's a two-part series. So in part one, we'll be doing introduction, what actually linear regression is. Logistic regression is, and also probabilities and odds. In part two, we're going to run an R program output and interpret the results. That can be very tricky also. So let's start our logistic regression with one simple example. It's kind of a fun example just to give an idea what it is. So I'm assuming or imagine a husband and wife are roaming around in a upscale mall. They go to a store, a women's store, and here are the two scenarios. Regression. Husband has a regression equation. These are mental regression. You're thinking about mentally. And wife has regression equation also going on. Same thing, mental regression. What husband is thinking, what husband trying to calculate. Given the upscale store, given the other prices of the items, given the brand, how much will this purse cost me? Okay. What's wife thinking? Given my approaching birthday, given his promotion, given my friends got nice purses, what's the likelihood this is going to be my surprise gift? Both are thinking different things about the same purse. So husband's answer could be $500 to $5,000. I mean, purses cost a lot more than some of them. Okay, that's his regression outcome is. How about wives? 0 to 100%. Probability of it becoming a gift for her, right? So this is we normally have linear regression or non-linear regression or something of that sort. This is what we have logistic regression. What's the difference here? Output is always between 0 and 100%. In this case, can be any number. Price of a house could be anything. Price of a used car could be anything. Price of a purse can be anything. But here, it's always 0 and 100%. So where do we use it? Lots of places. Let's say your loan approval. You go to a bank, apply for loans. Bank may refuse you. Bank may say, yes, we can give you the loan. Well, the output of that regression program they have is between 0 and 1. If the probability of you paying the loan back is suppose 80%, you get the loan. If it's a 10%, you won't get the loan. So again, 0 to 1. About emails, spam versus not spams. About admission to an MBA program. Will the student be able to finish it? Again, probabilities. So lots of places we use it. Machine learning, where machines decide yes or no. Medical diagnosis, banking, engineering, marketing, politics, etc., etc. So it's pretty widespread model actually used. So output now depends. The output is between 0 and 1. But how do we do it? It doesn't matter what you put in dependent variable. The independent variable is always between 0 and 1. How do we do that? We use sigmoid curve or S curve. It's also called logistic curve too. So that's the function. Now, if you can plug in any value of z here, you can try in Excel. The result will always be between 0 and 1, like in this case. 0 and 1. It will not go past. You can put minus 5,000, plus 5,000, it will be always be there. So this looks good. If we can have our dependent variable of this nature, we achieved it. But how do we do it? How do we incorporate it into our model? And answer is using probabilities and odds. Now we are going to discuss that first. Probabilities and odds. So here suppose we have a table, customer data. We had 510 visitors coming in, 265 female, 245 male, and some bought, some didn't buy. Here's the table. So we are looking at the probability of female purchasing and male purchasing. So probability of purchase given female is 0.6. That simply will be this divided by that. Not purchasing will be this divide by that. For male, this divide by that, and this divide by that for other things. So here they are. So if female, 60% chance she's going to buy, 40% chance will not buy. If male, smaller chances of buying, more chances of not buying it. So that's probabilities are there. Now what are odds? Odds basically will be purchase versus not purchase. P over 1 minus P, like that. So here is our table. So what are the odds of a female purchasing it? That will be 0.6 over 0.4, 1.5. Male purchasing is 0.815. So women is likely to purchase, man is not likely to purchase. Okay, that's what odds are. Odds ratio simply will be female versus male. So we have odds table here. So probability of female purchasing versus male purchasing is 1.84. So if there's a man and a woman in the store, there is a 1.84 times more likely probability chance that women is going to buy than the man is going to buy. And that's what odds ratios are. So a woman is 1.84 times more likely to purchase than a man. In logistic regression, we try to use our sigmoid function in this side here, log odds. What are the log odds? This one. Okay, that's the odds. Now, if you do reverse transformation, this becomes e to the power. Our base was e, basically. That's why we had it at the universal constant. So p over 1 minus p becomes e to the power this one. That basically means p equal to e to the power this plus 1 over e to the power this. And notice carefully, this is sigmoid function. E to the power z plus divide by 1 plus e to the power z. And if you plot this one, you'll get sigmoid curve like this one there. So basically our regression is on odds. So our dependent variable will be log odds, independent variables, whatever we have. And this is the idea behind logistic regression. So this is, we have log odds. This is also called logit P. In the next video, we are going to discuss our program and also the results. And that can be a bit trickier. So pay attention to that part. For this video, we are done right now, all done.